Well, welcome to The Boiling Point. I'm Richie Ware, and this is President of Victory Energy, John Viskup, and founder of Victory Energy. John, we have never been able to talk about an HRSG on The Boiling Point, and you have one in your shop. I wanted to talk about it, but maybe first, you cut your teeth on these things when you started the company. Maybe talk a little bit about that real quick.
Yeah, so we love to talk about the HRSGs, and Richie's right. It is the genesis of our company and how we got started, and quite honestly is, when we think about boilers, we think about heat transfer. It always starts with heat transfer. Yeah. And so in a heat recovery boiler, that's what we're focused on, is transferring heat. In the very beginning days of Victory Energy, we put an application with a waste heat boiler, a heat recovery boiler, that was able to produce steam for a processing plant. So it's, again, the idea behind it is capturing heat that's otherwise discharged to the atmosphere, putting that heat over some tubes and producing steam or hot water or whatever the case may be. If you look at all the available heat sources within America, in this particular application, this is off a calcining process, which ultimately produces aluminum for a customer. And we're taking heat that comes off of their furnaces, million pounds per hour of flue gas, at 1450 degrees Fahrenheit, that for the last 50 years, they discharged it out the stack. You talk about reducing your carbon footprint. Sure. We took all of that heat, we will put it over all of these particular tubes in the boiler, and we're gonna produce, upwards of 150,000 pounds per hour of steam, which is gonna produce electricity, and through the letdown process of the steam turbine, we're gonna actually provide process steam for the plant. So it's a dual application for us. Yeah, but in particular, this is off of a calciner, and heat recovery boilers, as you mentioned, is in multitude of applications. Whether it's on the backside of a gas turbine in a clean application is one example, and other examples could be all kinds of processing plants in the production of ethanol. They use it in a distiller grains dryer application, but there's several, so many.
So I wanted to come around the side of the boiler and actually get a little bit closer look at these tubes, because this is pretty cool, all right, the way that these tubes are made. So go ahead and tell us a little bit about those.
Yeah, so as you would typically see in a standard industrial boiler, you wouldn't necessarily see these kinds of tubes. We use a bare tube, but in a heat recovery application, the idea behind it is we're trying to absorb as much heat as possible, from the flue gas into the tubes. And so we use a process called a finned tube. In this particular finning, because it is a dirty gas application, we are using a solid fin, and there's other kinds of fins like C-aerated fins, which we would use in a natural gas type setting. Right. But in a dirty gas setting, in this particular boiler, we're using a solid fin, and you can see by the pitch of the fin, or the height of the fin, it's very short. Right. And therefore, again, in a dirty gas application, it's easy to clean. Okay. So we're maximizing heat transfer with extended heating surface by the way of a fin tube, still using a standard boiler tube, which just is welded to it, to produce steam.
Now, you brought up a point here that you said you got to clean them. How does that happen?
So yeah, great question. So how we clean a fin tube in a dirty gas application is through soot blowers. Okay. Soot blowers could be done with air or steam. In this particular case, we're actually using steam. Okay. And so steam will come from the process or off the drum. It is fed through, we call them mechanical soot blowers that are strategically put into the boiler at various locations to ensure cleanliness. Okay. And as we remove the soot off these tubes, we're able to regain the heat transfer that is potentially lost through the fouling of the tubes through the fitting.
So if you don't clean them, then what?
If you don't clean the tubes, what you'll see is on the back end of the boiler, the temperature will rise over a period of time. And as that temperature is increasing, your thermal heat transfer efficiency is decreasing. All right. And so the idea is the cleaner we can have those tubes, the more heat we can transfer into the water going through the tube, and the more efficient steam that we can produce.
Awesome. If they don't get cleaned up, I mean, can there be some fouling of the tube?
Absolutely. So what you'd find is if you don't have a good cleaning process in your operation, the tubes will foul. And eventually, as they continue to foul, and if that soot continues to build up, you could find localized tube failures, ruptures in the tubes, splits in the tubes, where essentially what's happening is The goal in any kind of heat transfer design is to keep that tube surface as cool as possible.
Right.
And the way to do that is to ensure that you have good natural circulating water behind it and a clean tube to make sure that this tube metal temperature is below the allowable limits for carbon steel. We've produced boilers that can produce over 2,000 PSI steam pressure. So very, very high, also in a superheated application. In this particular unit, it's over 1,000 PSI.
Very cool, awesome. Well, once again, steam is cool. A lot of people don't think that, but we do, right?
Right.
Right.
Of course.
Well, appreciate you hanging out with us, John, and we'll see you next time on The Boiling Point.